So we're going to introduce acids and bases. This is fun chemistry when we're in the lab, and actually after this week I will allow you to do some fun acid-base chemistry at home. That's quite easy to do, but right now I want to introduce you to the concepts and the math involved in the concepts of acids, bases, and pH. So acids are around you in your everyday home life. You've got vinegar, which is acidic. You've got baking soda, which is basic. So acids and bases are common. In fact, almost everything can be classified as somewhat acidic or basic when you get down to the higher level of acid-base chemistry. So oranges and your fruits have ascorbic and acetic acid. Battery acid is primarily sulfuric acid. Ants, when they sting you, inject formic acid. That's where the burn comes from. You have things that are strong acids, like your battery acids, and of course, in the laboratory, we have HCl. You have weaker acids, like your ascorbic and citric acid, and then you also have substances that contain organic acids, this group like here, like aspirin. Aspirin is a weak acid. Weak and strong acids are defined by how many hydrogen ions they produce. The hydrogen ion is what makes something acidic, so how many of those ions are present is what gives you a strong acid versus a weak acid. Properties of acids is that they taste sour or tart. They do conduct electricity in solutions. Those are things that we call electrolytes, conducting electricity in solutions. Most of your acids will react with metals to form hydrogen gas. We used hydrochloric acid in the lab to make our hydrogen with zinc metal, and they change indicators different colors, which is one of the enjoyable parts of acid-base chemistry, and we'll look at some labs that you can do at home for that. And of course, acids and bases react to form salts and waters from your study of reaction types. So when you're looking at, so here's the structure of nitric acid, and here's sulfuric acid. Notice you have two hydrogens. Those are your hydrogens, the white, and then for phosphoric acid, you have three hydrogens. In these types of acids, your hydrogens are always bonded to an oxygen atom. So the hydrogens are bonded to the oxygen atoms in these acids. Your common acids that you would see in the laboratory are hydrochloric, sulfuric, nitric, and of course acetic acid. And vinegar is 7% acetic acid. So most of us have vinegar in our kitchen cabinet. So when we study acids and bases, we'll use that as our acid. Your bases are things like bleach and ammonia. Drano, soap is a base. So these are your common bases. In the kitchen chemistry that we'll do next week, we'll try to use ammonia if you have that present. Windex contains ammonia, so you should be fine. Bleach is a little more dangerous to use and a little more corrosive, and Drano I would not want you to use at home. So ammonia is one of the safest bases, and of course you could even use soap solutions as well. So your bases taste bitter. I'm not advising you to go lick soap, but if you did touch your tongue to soap, it would taste quite bitter. They feel slippery, so you know that soap feels slippery, and if you've ever spilled bleach on your hands, you know you have a tough time washing it off. They also conduct electricity in solution, and they change indicator colors, and they react with acids to form salt and water, so acid-base chemistry. So a neutralization reaction is the reaction between an acid and a base to form a neutral saltwater solution if you add just enough acid and base. So the salt doesn't have to be the salt that you think of as sodium chloride. Remember your chemistry, a salt is any ionic compound. So you are changing the acidic and basic pH to a neutral pH. Acids and base make salt and water. So now let's go into more depth of studying what makes these species acids and bases. So we often use the hydrogen ion when we talk about our acids, but actually there is no hydrogen ion. It's always the hydronium ion. The water molecule grabs that extra hydrogen that is floating in the water and pulls it into its structure. So if you took the basic bent hydrogen structure, let me try to draw this out. I won't put the dots on the oxygen. I might. Let me go ahead and put those lone pairs of electrons. So your water molecule will grab this extra H plus and bond it right here, making a trigonal pyramidal hydronium ion structure. So your hydronium ion is often called the hydrogen ion, but it is not. So we often write H plus as a shortcut, but just remember there is no H plus. It is always the extra H plus is grabbed up by the water molecule to form the hydronium ion. So chemists will sometimes take a shortcut of just looking like you have the acid falling apart to these ions, but in fact it doesn't work that way. The water grabs this hydrogen ion, forming the hydronium ion and leaving behind the chloride. So in our next week's lesson, we'll focus on this mechanism that takes place between acids and bases and water. So H plus is an abbreviation, but the hydronium ion is better chemistry. So here we've got water reacting with water. So water can act like both an acid and a base. So in your beaker of water, you have primarily water molecules, but a few of them, and you'll watch a video where you get the water molecules colliding with each other and transferring that proton from one molecule to another, forming the hydronium ion, and in the other molecule, leaving behind the hydroxide. This is going to lead us to the understanding of what pH is. In neutral water, you have equivalent amounts of hydronium and hydroxide ions, and that amount is very tiny. It happens to be 1 times 10 to the negative 7. So we'll learn how we're going to take a log function of that number, that 1 times 10 to the negative 7, and turn it in to what we refer to as the pH of neutral water as 7. So let's watch the molecules collide as they transfer that proton. So there are your water molecules, and you've got a very few number of hydronium and hydroxide ions, but as the water molecules collide, one of them transfers its proton to another. That leaves it with the hydroxide ion and gives the hydronium ion, and then you often get them colliding back and reforming water. You do primarily have more water molecules. We said you only have 1 times 10 to the negative 7 moles per liter, or molarity. This was one of the reasons for you to learn molarity. The concentration of the hydronium and hydroxide ions are equivalent in neutral water, and they each have a molarity of 1 times 10 to the negative 7 moles per liter, or a molar solution. Here's another video of that transfer of that proton that goes on and on in any sample of water. This is always occurring, and in any sample of neutral water, you always have 1 times 10 to the negative 7 moles per liter of those ions. So that common pH range takes you from where your hydrogen ion concentration is greater to where your concentration is equivalent to where your hydroxide is greater. The common pH range goes from 0 to 14. But you can go outside of that range, as you will see when we start applying our math. But the common pH range goes from acidic at 0 to 6.9 if you want to get that specific, and then 7.1 to 14 is your basic. So pure water is neutral. Those concentrations are equivalent, and they are equal to 1 times 10 to the negative 7 at 25 degrees Celsius. Now, we don't get in at this level too much to the temperature effect on pH. That's more of an AP level. It's not a huge change, but temperature does affect the number of ions slightly. So your neutral solution has an equivalent amount, and it's that. So if you have hydroxide ion that's greater than that, you're basic. And if you have hydronium ion that's greater, you're acidic. So here's your acidic end of the scale. As your hydronium ion increases, your pH decreases. So we're going to need to look at the math and understand why that is. It's not intuitive for you to understand. We need to learn that this lowercase p is a log function, and mathematically it's going to create an inverse relationship for us. But right now, as we are more acidic, we have more hydronium ions, our pH is going to get lower. For a basic solution, as we have more hydroxide ions, then the pH increases. So pH increases with more hydroxide ions. It decreases with more hydronium ions. So your basic range between 8 and 14 has an hydroxide ion concentration greater than 1 times 10 to the negative 7. So just what is this pH? Somewhere in your science background, someone has told you it's the power of hydrogen. That couldn't be more wrong. Maybe they're just trying to make it stick. That's not it, so don't think that. This P is a math function that means taking the negative log base 10 of a number, the lowercase p, and it is a lowercase p. You do not write pH with an uppercase. It's telling you take the negative log of the hydrogen ion concentration. What it really does is turn a very small exponential number into a whole number rather than these tiny exponential numbers. So let's look at what we are going to do. The video that I have made for you after this goes into more depth on that math, and I show you the calculations on my calculator so that you can go along with them. If you don't have any trouble doing it with this explanation, that's fine, but you still need to watch the next two videos that go into the application of this math. So the lowercase p means to take the negative log. You would hit the negative button, not the minus, the negative button, and the log base 10, not the natural log. So if you're trying to put in p, you hit the negative and then your log button. So if I want to know the pH, I take the negative log of this hydronium ion concentration. The hydronium ion concentration, and sometimes we might abbreviate it, the H plus concentration. Remember, they mean the same thing. So the brackets mean the molarity. You can't just negative log anything and come up with a pH. It has to be the molarity of the hydronium or hydrogen ion that's in the solution. So what is the pH of a solution that contains 1 molar hydronium ions? So for the math of that, you would use the equation, negative log, and you would put in the 1. Now you do not need to type in the brackets. We are writing the brackets to indicate molarity. You don't type them in. So just hit negative log of 1 on your calculator. Give you a second to try that if you have your calculator present. When you do take negative log of the number 1, you're going to get a pH of 0. So a pH of 0 is what you get when you type in negative log of 1. Let's look for some patterns here. What is the pH of a solution that contains 1 times 10 to the negative 1 moles per liter of hydronium ions? So this time you're going to take negative log of 1 times 10 to the negative 1. So hit your negative log, and then just type in the number, no brackets, 1 times 10 to the negative 1, which is, of course, 0.1 if you want to do it that way. Negative log of 1 times 10 to the negative 1, or negative log of 0.1 should give you a 1. So what the log function does is it takes this exponential number and turns it into a whole number. Notice here, this was to the 0 power, okay? So negative log of 1 is going to give you 0. This is to the first. So if you've got 0.1, if you're not writing it in exponential notation, then you're not going to necessarily see that this exponent becomes that pH. Let's do a few more. So what's the pH if you have 1 times 10 to the negative 2? Well, if you're following the pattern, that's going to give you a pH of 2. So the whole purpose, when you're dealing with pH values and acid-base solutions, you have very, very dilute solutions. They are to the negative 2, negative 3, negative 4 molar. So instead of having to write those concentrations to tell you, because pH is telling you the concentration of hydrogen or hydronium ions, this P function, this negative log, is turning that exponential number into a nice user-friendly number. So by now you should recognize 1 times 10 to the negative 3 has a pH of 3. And now what's going to happen? So let's go back. So these were all 1 times 10 to this exponent. So 1 times 10 to the negative 4 would have a pH of 4. 1 times 10 to the negative 5 would have a pH of 5. But what if we're not 1? What if we're 2 times 10 to the negative 3? So before we punch it in, let's look. We have a greater ion concentration. We have more hydronium ion. And we said, since this is an inverse relationship, if this number becomes greater, our pH should become smaller. So if you take the negative log of 2 times 10 to the negative 3, you should expect to get a pH less than 3, and you will. You will get a pH of 2.7. A pH of 2.7 relates to a hydronium or hydrogen ion concentration of 2 times 10 to the negative 3 moles per liter, which is more moles per liter of hydronium ion and a lower pH. That is why this is an inverse scale for the hydronium ion. So let's keep going. What if we have a 3 times 10 to the negative 3? So back here, at 1 times 10 to the negative 3, we were 3. At 2 times 10 to the negative 3, we're 2.7. We certainly should be lower. Give yourself an estimate and then punch it into your calculator. Negative log of 3 times 10 to the negative 3 is going to give you a pH of 2.52. pH values are almost always rounded to 2 decimal places, so you will see that I do that fairly consistently. What about 4 times 10 to the negative 3? So we've got more hydronium ions, so we should have a lower pH, and we do. So I'm going quickly through these. Of course, you can always pause the video and try it out, but the practice will come in the next 2 videos after this so that you get a chance. This is just an introduction to how this logarithmic scale works for you. So, as we looked at our results, our hydrogen ion concentration, we had more hydrogen or hydronium ions floating in water, and our pH went successively down as our concentration went up. So more acidic has to mean lower pH, and it has to mean we have more hydrogen ions. That just makes sense. But because of that logarithmic scale, we get that inverse relationship. You probably already remember that from middle school. They may have explained the math to you, or they may have just said, as pH goes down, you get more acidic. But now you know that pH is actually a mathematical log relationship that converts an exponential number into a more user-friendly number and still relates that number to the amount or concentration, which you learned in the last lesson, of ions. So let's see if we can determine the pH of each of these solutions. So if your hydrogen ion concentration is that, then you're going to negative log that number. So again, I'm going to go through these pretty quickly. If you want to follow along and pause, you may. So on your calculator, hit negative, your little negative sign, and your log base 10, and then just punch in 4.6 times 10 to the negative 5 and report it to 2 decimals. Look at the logic. If this was 1 times 10 to the negative 5, this pH would be 5. But since this is larger, this pH goes down from 5 to 4.34. It is an acidic solution. 2.7 times 10 to the negative 9. Now, before you hit this, look at this concentration. This is a very small concentration of hydronium or hydrogen ion. So if you were looking, if this was 1 times 10 to the negative 9, you would have a basic solution of a pH of 9. This is slightly more concentrated in the hydrogen ion. So if you punch this in, hopefully you are predicting that you're going to get a pH close to 9, but less at 8.57. Now that is a slightly basic solution. Okay? Remember, pHs over 7 are basic. So as you become more familiar, you can look at the exponents and begin to predict that this would be a basic solution. Here, we've got a negative 3. This is going to be quite acidic. It's not going to have a pH of 3 because it's more concentrated than that, but it's going to be pretty close at 2.74. So as you become more familiar with how these numbers connect to these, you're going to be able to understand your acid-base chemistry. It takes a while. It's brand new information. To go back and forth between those concentrations in pH takes some practice. So what if we have the pH and now we want the molarity? So remember, we took the negative log of the molarity to get the pH. Okay, so to get the concentration, we're going to raise 10 to the negative pH. So this is called the anti-log. Anti-log. The anti-log on your calculator is the second function key and then the log key. So let's look. The anti-log of the negative pH is going to give you the hydronium. So remember, the negative log of the hydronium gave you the pH. The anti-log of the negative pH is going to give you the concentration. The anti-log is the second key. So you've got your second function key. Hit second and log, and you're going to see the little 10 and the little caret's going to come up, and then you're going to put the negative pH in there, the negative pH, and that is going to turn that into the hydronium ion. So let's try this. So if the pH is 11.2 and we want to know the molarity of this solution, we're going to take the anti-log of the negative 11.2. So anti means second function, so hit your second key and your log base 10, hopefully you're not using your natural log, hit second log and then punch in negative 11.2 and you're going to get 6.31 times 10 to the negative 12. That's your molarity. That's your concentration. So you have a very small concentration of hydronium ion because actually you're a basic solution. So you would expect very little hydronium ion. Let's try another one. So we have a pH of 2.74 and we want the hydronium ion concentration. So on your calculator, second log, so second button, top left corner, okay, second log, and then put in negative 2.74. to give you a molarity of 1.82 times 10 to the negative 3. Notice your hydronium ion concentration is much stronger. Remember, a negative number. This is a very small number. The larger your negative number, the less concentrated or the smaller it is. And one more. So this would be 10 to the negative 8.85 gives you the concentration. So if you have the concentration, and you can do that right now, if you take the negative log of 6.31 times 10 to the negative 12, you should come back out to 11.2. You may have a little rounding difference there. If you take the negative log of this, you should come back to this. If you take the negative log of this, you should come back to that. If you anti-log the negative of this, you should get that. If you anti-log the negative of this, you should get that. If you anti-log the negative of this, you should get that. So negative logging and anti-logging the negative take a little while for you to not confuse them. But what if you have a base and not an acid? So up till now we've looked at pH, the negative log of the hydronium ion concentration. But if we have a base, okay, we can't just take the negative log of the base, remember bases have hydroxide ions, and expect to get pH. We don't. We get POH. Now, you may not have been aware there was another acid-base scale. Most people don't. Even chemists don't think in the POH scale, but you have to use the POH if you have a base, and then you will convert it to the pH scale. So let's look at what we're talking about. So if we take the negative log of the acid or the hydronium ion, we get the pH. And of course, in neutral water, we have a pH of 7 because the hydronium ion is 1 times 10 to the negative 7. But there is another scale. If we have a base and we take the negative log of the hydroxide ion, we get the POH. And in neutral water, that is still 1 times 10 to the negative 7, and we get a POH of 7. So neutral water has both a pH and a POH of 7, and the concentrations of the hydroxide and hydronium ions are equivalent at 1 times 10 to the negative 7. The pH and the POH together add up to 14, and you'll see why that is quite useful as we work through some problems. Now remember, this is probably more complicated, so I do spend quite a bit of time in my next videos showing you the math, having the calculator under the document projector so that you can see what I'm punching in. So this is just to set you up for that process. So let's look at the POH scale. Remember, if we've been given a base, then we have to use the POH scale. So if we have 0.1 molar sodium hydroxide, we can do the negative log of that. Go ahead and take the negative log of that. It's still going to give you a 1. That's great. Your calculator doesn't know acid-base chemistry. All it knows is the negative log of 0.1 is 1. But you know that this is not an acid, that this is a base. So when you negative logged that number, you found not the pH, but the POH. To find the pH, you use that simple, that fact that the sum of the pH and the POH is 14, so 14 minus that 1 gives you that nice basic pH. Everyone thinks in the pH scale. So a pH of 13 is clearly basic. We know that. But if given the concentration of the base, only the chemistry person knows where that 13 actually comes from. So a pH, okay, of 13 is a POH of 1. And why did we have to find the POH? Because we had a base. Remember, the negative log is going to give us the 1. You can't say that this base solution has a pH of 1. That doesn't make sense. You can't give a base an acid pH, but you're not saying that. You're saying this is the POH. There's the OH there to remind you. and then you subtract from 14 to get the pH. So let's look at this problem. If we had the hydroxide ion, so if this was sodium hydroxide, and we had a 1 times 10 to the negative 3 molar, we still know what our calculator is going to tell us. If we take the negative log of 1 times 10 to the negative 3, it's going to give us a 3. Okay? But that 3 is not the pH, that's the POH. So we subtract from 14 to get the basic pH that we expect, which is 11. Let's look here. 2 times 10 to the negative 3. So if you've got your calculator out, you know, okay, that if you have 2 times 10 to the negative 3, you're going to get a smaller number than 3. But this is going to be your POH, okay? When you subtract that from 14, you're going to get a larger pH, which you expect because you have more concentration of hydroxide ions. So your relationships, let me go back. I thought I had another one here. So for your hydroxide, there's one extra step. You have to recognize that it's a base. First of all, your calculator doesn't know that. It's just going to put in the number. Negative log of 1 times 10 to the negative 3. It's going to give you a 3. If you say a sodium hydroxide concentration is a pH of 3, then you're not doing the chemistry. The sodium hydroxide is a base. Bases have pHs greater than 7. So to get that pH, subtract from 14. Here, get your POH, and to find your pH, subtract from 14. We agree, everyone thinks in that pH scale, but if you have a base, that calculation starts out in the POH scale. So here are all of your relationships, and they are given to you on all of your worksheets. To find the pH, you take the negative log of hydronium. To find the molarity, you take the anti-log of the negative pH. For the hydroxide, you take the negative log of the hydroxide. Okay? To find the OH negative, you would raise 10 to the negative POH. Then, if you have to find the pH from the POH, you use this relationship that the sum of them is equivalent to 14. Anytime you have a neutral solution, these concentrations are equivalent. Anytime you have more hydroxide, then this number is larger. Anytime you have more hydronium, then this number is larger. So there's plenty of practice in the next 2 videos to get the math of this down. So acidic pHs have an increase in hydronium and a decrease in pH, and basic solutions have an increase in hydroxide and an increase in pH. These are exponential factors, so let's look. If you have a solution that's 1 times 10 to the negative 6, it has a pH of 6. We know that from having looked at our calculator problems. If we change that molarity tenfold, so from negative 6 to negative 5, that's a tenfold change. That's 1 pH unit. So for every 1 pH unit, you get a 10 times more concentrated solution. So sometimes when people say, oh, between 5 and 6, that's 10 times as concentrated. Okay? If you go to a negative 4, okay, from a negative 6, that's again 100 times more concentrated, is 2 pH units. So again, for every tenfold concentration change, power of 10, you get 1 pH unit. So from 6 to 4 is 100 times more concentrated. And from a 6 to a 3 is 1,000 times more concentrated solution, but only 3 pH units. So your pH units, for every pH unit, that means a tenfold increase in that hydrogen ion concentration. So let's look at a summary that kind of looks at all of these acid and base properties as well as some application.
From the tangy bite of a piece of fruit to the caustic liquids used to clear a clogged sink, acids are a type of chemical that could be found in many different aspects of our daily lives. But what is it about acids that makes some safe to eat and others dangerous? When talking acids, we're going to be talking hydrogen. Not the gas, but rather the hydrogen ion H+. This is a hydrogen atom that has lost its one and only electron. All acids produce H+ ions when dissolved in water, but it's how much H+ a specific acid can produce in water that will determine whether it can be safely eaten or not. But how do we conceptualize and measure H+ concentration? Søren Sørensen, a Danish chemist, pondered this question when he worked at the laboratories of a commercial brewery in Copenhagen. It was in 1909 that he developed a method of quantifying acidity, what is now known as the pH scale. His scale works by simply converting the concentration of hydrogen ions in a solution to a number between 0 and 14. If a chemical is acidic, then its pH will always be below a 7 on the scale. The lower the number, the higher the hydrogen ion concentration. The pH scale is a logarithmic one, meaning that 1 unit difference on the scale, say from 3 to 2, means a 10-fold difference in H+ concentration. But 0 to 7 is only half of the picture. So what about all these numbers above 7? Substances that correspond with this half of the scale are called bases, and they are the chemical opposites of acids. The 7 on the scale represents neutral pH, what would be perfectly pure water. Like acids, bases are found in chemicals that we encounter in our everyday lives. Cleaning products such as ammonia and baking soda are bases, as are some simple medicines like milk of magnesia. They're bitter to the taste and often slippery to the touch, kind of like soap. Even though bases are different than acids, they too can be strong or weak, and a strong base can be just as dangerous and corrosive as a strong acid. Chemically, the difference between acids and bases is that acids produce hydrogen ions and bases accept them. In water, acids produce H+ ions and bases produce OH negative ions. In reactions between acids and bases, hydrogen ions will react with hydroxide ions to make water. This type of chemical reaction is called a neutralization reaction. Acids and bases are also very important in biochemistry. Many biological processes are sensitive to the pH of the surroundings, so controlling acidity in the body is crucial. Some biologically important molecules like amino acids have dual personalities. They're said to be amphoteric, which means that they can act as both acids and bases. An amino acid has a carboxylic acid group that can produce hydrogen ions and an amino group that can accept hydrogen ions. Acids and bases are all around us and can vary greatly in terms of their use and their nature, but they all involve hydrogen ions being passed around. Thanks for watching. If you would like to learn more chemistry basics, make sure to check out these other interesting videos in the series.
So this should set you up for success in the next 2 videos.